Welcome to homework.
Okay, so in this exercise, we're going to talk about the oscillation of a rigid body. So first, remember that the equation of motion for the rotation of a rigid body is going to be the equivalent of Newton's second law, but for rotation. So this is equal to I, the moment of inertia, times the angular acceleration, and this is equal to the total torque acting on the rigid body. Also, remember that the torque is going to be equal to the cross product between a position vector, on which the position vector is going to be pointing from the center of mass of the rigid body up to the point on which the rotation is happening, with the force acting on the body. So, in this exercise, we have a non-uniform rod that can rotate around both of its edges, A and B. We know that that the distance between edge A and the center of mass of the rod is equal to RA, and the distance between the edge B and the center of mass is equal to RB. We know that when we put the rod to rotate around the edge A for small for small oscillations, we have that the period for the oscillations is going to be equal to 0.87 seconds. And when we oscillate, when we have small oscillations around point B, the period of oscillation is going to be 0.78 seconds. We also know that the total length of the rod, that is RA plus RB, is equal to 10 inches, which in the metric system is 0.254 meters. Okay? Okay. So the exercise also asks us to write things in terms of a quantity called K bar, that is the so-called centroidal radius of gyration. Okay, and the exercise wants us to find RA, RB, and K bar. Okay, so to try to find these values with the given quantities, we first can try to write the equation of motion for the rod. So dealing with the left-hand side first, we have that the equation of motion is going to be the total moment of inertia times the angular acceleration. In the case of the rod oscillating, around one of the edges, so we have the rod here in green, J is the center of mass, we have a small angle theta. So in this case, we have that when the rod is rotating around this point, the moment of inertia is going to be the moment of inertia coming from the center of mass plus mr squared, on which r is the distance between the point of rotation and the center of mass. This is just the parallel axis theorem. Okay, and we can rewrite the center of the moment of inertia of the center of mass in terms of k bar. So by definition, it's going to be like this. So the left hand side of the equation of motion is going to be equal to m times the angular acceleration times k bar squared plus r squared. Okay, now we have to look at the right hand side. So the right hand side is the total torque acting on the body. So let's think about what are the forces that are acting on the rod. So the only force that is going to act in this case is the gravitational force that is going to push going to be pointing downwards. I'm going to call it P. Now, we know that the definition of torque is the cross product between R and the gravitational force. So we know that since R is pointing in the direction of the length of the rod, we know that the only part of the gravitational force that is going to contribute to the torque on the rod is going to be the part that is orthogonal to the length of the rod. So I'm put here in red so you can see it better. I'm going to call this px. Okay? And we can find a relation between P and Px if we notice that this angle here is theta. This is a 90-degree angle, so this is also going to be theta. So that we have that Px, that is the only term of the gravitational force that is going to contribute to the torque, is going to be equal to P times sine theta. And in the limit of small oscillations, we have that sine theta is going to be roughly equal to theta. So Px is going to be approximately mg theta, on which g is the gravitational acceleration. Okay? So we have that the right hand side of the equation of motion is going to be simply r times mg theta. Okay, so let's put our equation of motion in here. So we have the left hand side is m times the angular acceleration times r squared plus k bar squared. This is equal to r mj theta. We can cancel out m in both sides of the equation, and we can pass this term to the other side of the equation dividing, so that in the end of our equation of motion is going to look roughly like this. So the angular acceleration. Another thing I forgot to mention. This is going to be a negative term here. And this is because px is going to be, by choosing a coordinate system that has the vertical axis parallel to the length of the rod, we're going to have that our px is going to be pointing to the negative x direction. So this is negative. Okay, sorry about that. So this is going to be equal to the angular acceleration plus j r over k bar squared plus r squared, and this is equal to 0. So this is the equation of motion for the rod when it's rotating around A or B. So in the case of A, we just replace R by RA. In the case of B, we just replace by RB. Okay? So we know that the term that is multiplying the displacement theta is going to be equal to the square of the angular frequency. So we can find the expression for the period of oscillation to be equal to 2 pi over omega. So we have 2 pi square root of k bar squared plus r squared over jr. Okay? So we know the value for TA and TB. So let's try to write the expressions. We have that TA is 2 pi k bar squared plus RA squared JRA, and TB is 2 pi square root of k bar squared plus RB squared over JRB. Okay, so let me call this 1 and this 2. And we also have the third expression. We know that RA plus RB is equal to 0.254 meters, or RB is equal to, I want to write as RA. So RA is going to be equal to 0.254 minus RB. So we can substitute the expression 3 in 1, and we are going to have something that looks like this. So taking the square of 1 and substituting 3 in 1, we have TA squared is equal to 2 pi squared times K bar squared plus RA squared, which we know it is 0.254 minus RB squared, over J RA minus B. Okay, so given that we know TA, we can try to find RB first. So let's try to isolate K in expression 1. And by trying to isolate K, we're going to find something like this. So we'll have K bar squared is going to be equal to TA squared over 2 pi squared times J 0.254 minus RB minus this term 0.254 minus RB squared. Okay, and just by substituting the values that we have, so TA and J, we're going to find that K bar squared is going to be equal to minus RB squared minus 0.321 RB minus 0.017. Okay, so we found an expression for K bar squared. I'll call it 4. So we can substitute the expression for K bar squared that we found in terms of RB back in expression 2, so that we are going to have an expression on which the only unknown variable is going to be RB. Okay, so putting 4 in expression 2, we're going to find that TB, let me write put in the square of expression 2, and I already substitute the values. So we're going to have that TB squared over 2 pi squared RB squared plus K squared, which is expression 4, minus RB squared minus 0.321 RB minus 0.017 over J RB. So we can cancel out RB squared. Okay, and substituting the values for TB, we are going to have that we are going to find that 0.17 RB is going to be equal to 0.017. Okay, so we find that RB is going to be roughly equal to 0.1 meters, which is equivalent to say that RB is going to be equal to 3.91 inches. Okay, and knowing that RA plus RB is equal to 10 inches, we are going to find that RA is equal to 6.01 09 inches. Okay, so first answer, second answer. Now we have to find K. And to find K, we can simply go back to expression 2 squared and substitute the value for RB, or go to expression 1 squared and substitute the value for RA. So I'm going to go to 2 squared, so to find K, so we have TB squared over 2 pi squared is going to be equal to K bar plus RB squared JRB. So let's try to isolate K bar. So K bar is going to be equal to TB squared times JRB over 2 pi squared minus RB squared. Now we just substitute the values for TB, J, and RB, and we are going to find that K bar is going to be equal to 2.8 inches. And with this, we conclude the exercise.